All right, it looks like everybody's joined here. I think it's time for us to get started. Thanks again for joining today. My name is Nate Rude. I'm a technical R&D and technical sales engineer on Variscite's software engineering team. And today I'll be presenting on how to get started with device tree development on Variscite System on modules. This is our agenda. I'll start by going into a brief Variscite introduction. Then we'll jump into an introduction on device trees. Then we'll move into some device tree fundamentals like syntax and driver usage. We'll walk through creating an example device tree for a custom carrier board. And then we'll finish by integrating our new device tree into a Yocto layer. Okay, so about Variscite. Variscite is a leading system on module provider selling over 1 million units per year. We have over 5,000 customers from diversified markets worldwide. We're the only system on module vendor that is an NXP platform member with the most diversified IOMUX-based portfolio. Variscite owns all of its production lines. This allows for easy customization and cost optimization for our customers. We're ISO 9001 and 1345 certified. Variscite's high quality customer support, long-term longevity, and ecosystem of partners ultimately provide a complete end-to-end solution for our customers. Okay, so Variscite primarily has two SOM families. One is named VAR-SOM, and the second is named the Dart family. On the top here, you can see our VAR-SOM modules. These offer scalability from the IOMUXC UL all the way up to the latest IOMUX 8M+. And in general, all of these modules are pin-to-pin compatible with each other depending on the PinMux options that you select. And then on the lower right is our Dart family. The Dart family has a smaller form factor, but actually provides more interfaces in the connectors than the SOM family. This family is also pin-to-pin scalable, depending on the PinMux options that you select. And it allows you to scale from the IOMUX 8M Mini up to the latest IOMUX 8M+. So again, both of these SOM families provide scalability and processing capabilities while maintaining the same interfaces and form factor. This allows you to scale from the A7 and A9 processing capabilities all the way up to the latest A53 on the 8M+, depending on your product and application requirements. Okay, so now let's move into the device tree introduction. If you're brand new to device trees, you might be wondering what a device tree is. Basically, a device tree is a data structure of nodes that describes the hardware configuration to the Linux kernel. Every device in the system is represented by a node. The device tree is loaded by the bootloader and parsed by the kernel at runtime. This allows a common Linux image to run on multiple boards of similar architecture. So I think the biggest thing is that in general, a device tree specifies devices that cannot be discovered in a generic way. So for example, the USB controller and the SoC must be defined in the device tree, but the USB devices themselves can be automatically discovered, so these do not need to be added to a device tree. This is kind of a 10,000-foot view of how device trees are used. Here we have two Variscite evaluation kits based on the IOMUX 8M Mini. On the left is the VAR-SOM with the Symphony board, and on the right is the Dart with the DT8M custom board. Since these boards both use the IOMUX 8M Mini SoC, they can use a common Linux image. However, the boards are different. For example, they have different UARTs for the Bluetooth interface. In the Linux console, they have different I2C devices. So we need some way to tell the kernel about each board's unique device configuration. And again, this is what the device tree is used for. So in the example here, both boards use a common Linux image. When U-boot starts, it passes a board-specific device tree file to Linux, which tells it about the unique device tree devices for each board. On the left, you can see U-boot loads IOMUX 8mm var som symphony.dtb, and on the right, it loads IOMUX 8mm var dart DT8M custom board.dtb. And these are the device tree files provided by Variscite for these evaluation kits. For Variscite's IOMUX 8 family, device tree files are located in the Arch ARM64 boot DTS freescale directory inside the kernel tree. Here we can see the same device tree files from the example in the previous slide, as well as a few new ones. In general, device tree files are built by combining several files together. So for example, looking at the diagram here at the very top are the device tree files for the two carrier boards for the evaluation kits we just looked at. We have one for the var SOM on the Symphony board, and again, one for the var Dart for the DTS custom board. We can see moving down to the middle here that these device tree files include a common device tree file for the SOM. So we have included files that are specific for each SOM, in this case, the var SOM and the var Dart. And these include files basically include all of the devices that are unique to the SOM. And then all the way down at the bottom, we have SoC specific include files. In the example here, we have IOMUX8mm.dtsi, which should be included by any device that uses the 8M Mini. And this device tree file is provided by NXP. So generally, when creating a custom carrier board that uses a Variscite SOM, it's best to create a carrier board level device tree file similar to the Symphony and custom board files, and then include the SOM level device tree file from Variscite. Okay, so now let's jump into some of the device tree fundamentals like syntax and driver integration. This slide here shows the general device tree syntax. Device tree is simply a tree structure of device nodes and properties. The syntax is very similar to JSON, if you're familiar with that. At the highest level are device nodes. It's possible for device nodes to have labels, which can be used to reference them from another device node. Each node will have a unit address. Generally, the unit address is the primary address used to access the device found in the reference manual. Properties are simple key value pairs with several different formats. There are string properties, there's byte strings, cell properties, as you can see here. There's also p handles, which again allow you to reference a label from another node. Here in this example, we have a root node that has two child nodes called node and node 1. Each of these also have child nodes with their own properties. These are just example nodes. They don't really do anything specific. It's just used to demonstrate the device tree syntax. If you're wondering how we know the specifics for how to add new device nodes, we'll see later how to use the device tree bindings documentation to figure out how to write a new device node and which properties are required and optional and so forth. Okay, so now let's walk through several device tree examples to demonstrate some of the device tree fundamentals. This here is a simple hello world device tree file. It has a single node with a string property 1 set to a value of hello world. We can use the device tree compiler to compile this to a .dtb file, which is the format that's expected by the kernel. For the rest of the presentation, we can also compile it to a .dts file and print the output to the console in source format, which will be helpful for us to demonstrate the device tree syntax and inclusion principles in the next slides. In this example, since it's such a simple hello world file, we can see that the compiled output simply matches the input. Building on the previous file, here's an example that shows how labels work. We can assign a label to node 1, and then we can reference the label later in the same file or in a different file. In the initial node 1 definition, we add a property called string property 1, which is set to hello world 1. And then later in the file, we use the label as a p handle to modify node 1 by adding a second property called string property 2. And we can see at the bottom when we compile the device tree file, now we can see that the compiled node 1 has both string property 1 and string property 2, and that the device tree compiler has basically merged these properties together underneath node 1. Here's another example with labels, except for now we've used an include file. So in hello world 2.dtsi on the right, node 1 is defined again with string property 1 set to hello world 1. And it has a label called my node 1. On the left, In hello world2.dts, we use the mynode1 label to modify the string property. So instead of adding a property this time, we can also modify a property. And again, at the bottom, when we compile hello world2.dts, we see that string property 1 is modified with our new value. This is one of the common strategies for extending and modifying device tree files. So for example, you can use this method to include Variscite's device tree files and modify them for your custom carrier board. Okay, so now let's look at how device tree files or device nodes and device drivers are binded together. In this example here, we modify Variscite's device tree file for the IOMUX 8M Nano VAR-SOM Symphony board, and we add a new node called node 1. We set the compatible string for node 1 to hello world. The compatible string is generally what's used to bind a device node to a driver. On the right is an example of a platform driver. We configure this platform driver to match the hello world compatible string. So this driver here is basically just kind of a bare bones driver used to demonstrate how we can bind a device node to a device driver. As you can see again, we match the compatible string with hello world. So if the node is enabled on the left in the device tree and the compatible string matches in the driver, the kernel will call the probe function for the driver when the driver is loaded. For this driver, the probe function simply prints hello world probe. And as you can see on the left, when we load the driver, hello world probe is printed to the console. So building on the previous example, let's look now at how the platform driver can read device node properties. Here we add a property on the left of the device tree called string property 1, again with a value of hello world. And then in the driver on the right, the probe function is always passed a pointer to a platform device structure. And we can use that pointer to read properties of the device node. So for example, the probe function here reads string property 1 and then just simply prints its value to the kernel log. And we can see on the lower left, when we load the driver, indeed, hello world is printed to the console. This just kind of shows how platform drivers are able to be binded to a device node and access the properties underneath that node. Okay, so we've walked through several examples showing some device tree syntax, how device tree inclusion works, and how device nodes are binded to platform drivers. Again, these were just generic examples made up with made-up nodes and properties. And so for real devices, we need to know, how to write and how to add new device nodes. To do this, we can use the documentation within the kernel itself. All device tree bindings recognized by the kernel are documented in the documentation device tree bindings directory. And this documentation will generally give us a description of the device. It'll tell us which properties are required, which are optional, and in general, it'll give us an example device node that we can use as a reference. I also want to note it can also be very helpful to search other examples within the kernel itself. In general, there's probably a working example on a similar platform that may give hints or clues if you're stuck trying to add a new device. And in a few slides, we'll walk through an example that will show us where to find the device tree bindings for a specific device. Okay, so now let's walk through adding a new device tree file for a carrier board based on Variscite's IOMUX 8M Nano SOM. So what we'll do is we'll create a minimal device tree file that will boot for Variscite's VAR-SOM MX 8M Nano. We'll look at how to compile this device tree and then how to install and boot this device tree on the evaluation kit. And then I have examples that we can walk through for how to add a new I2C device to our device tree, how to add a PWM device and a PWM backlight device. For the purpose of this presentation, I'll only have time to walk through adding the example I2C device, but at the end, I've attached the examples for the PWM and PWM backlight, and you'll be able to download these from an email after the presentation. Okay, so the first step is to make and boot a minimal device tree file. So what we'll do is we'll clone the Linux IOMUX project from GitHub from Variscite. and then we'll create a new file called IOMUX var som symphony webinar.dts. And in this file, we'll add, again, just the minimum nodes necessary to boot. So at the top here, we can see our minimal device tree file includes the SOM level device tree file from Variscite called IOMUX var som.dtsi. And this includes all of the SoC specific device nodes from NXP, and also has all of the nodes necessary for the devices in the SOM, such as the PMIC, the IOMUXC, the LVDS bridge, etc. Moving down, it adds a model string. This model string can be read from the /sys devices SOC0 machine file in the root file system. It also adds a compatible string for the SoC. And then finally, we have two nodes for UART4 and UART4's IOMUX configuration, which is necessary for the Linux console on the evaluation kit. So again, this is just a bare bones minimal device tree file that we can boot for the ADEM Nano SOM. So now let's look at how to build this new device tree file. The first step is to add the device tree file to the make file. When we were going through the fundamentals earlier, we looked at manually using the device tree compiler to compile our device tree files. However, Linux has a make target that simplifies building device tree files and their dependencies. So again, in step one, we add our IOMUX var som webinar device tree file to the make file. In step two, we set up the build environment. The SDK in this example is provided by the Yocto populate SDK target. If you're not familiar with how to get access to this, you can visit our wiki to see how to use Yocto to build the SDK for your device. In step three, we build the device tree file. Basically, we just need to run make IOMUX8 var defconfig and then make DTBS. And again, if this process is new to you, you can visit our wiki to see how to build and install the kernel image and modules and device tree files as necessary. And then finally, in step four, we can see that after running make DTBS, indeed our new webinar.dtb file was built. Okay, so now let's look at how to boot the device tree file. Again, this process is fully documented on our wiki if you need more information or details. In step one, we'll use SCP to send our device tree file to the boot directory on the evaluation kit. In step two, we configure the U-boot environment to load this device tree file by using the fwset environment command to set the FDT file environment variable in U-boot to point to our new device tree file, our webinar device tree file. In step three, we reboot the board. And then finally, in step four, we can verify that we're booting our updated device tree by reading the machine file. And when we do this, we can see it matches the string that we defined in the device tree file. Okay, so now that we've built and booted our device tree file, before we add any new nodes, let's first explain the UART4 pin configuration. In general, most SoC pins can have multiple functions and settings. For IOMUX8, generally the SoC pins can have up to 8 alternate pin modes, but only one function and setting can be used on a pin at a given time. So generally, any device node that uses such an SoC pin requires a pin control configuration. And this configuration has to set up the pin function. Again, IOMUX8 can have up to 8 alternate pin modes for each pin. And then it also needs to set up the pin setting to enable pull-ups, pull-downs, drive strength, or any internal pin configurations. When we do this, before the driver is probed, the Linux device core will call pin control bind pins, and this will tell the SoC specific driver to write the pin configuration to the pin registers. So at the bottom here, if we look at the pin control bindings, pin control binding documentation, we can see we have to provide two properties. The first property is pin control names, which is a list of names for each of the pin control states. And then the second property is pin control N, which is a list of one or more P handles, each pointing at a pin configuration node within a pin controller. As I mentioned, with the pin control names, it's possible to have multiple pin control states. So just to demonstrate this further, I have two other examples here. One is an I2C example and one is an MMC example. We can see for the I2C example that pin control names now has two states. There's a default state, which configures the pins for the normal I2C mode, and then there's a GPIO state, which configures the pins as GPIO. And the GPIO state basically allows the I2C driver to recover from any kind of I2C bus contention. In the MMC example, we can see there are three states. There's a default state, a 100 megahertz state, and a 200 megahertz state. And basically this allows the MMC driver to reconfigure the pins for any speed mode changes that it needs to configure the speed for the MMC interface. Okay, so as the pin control documentation says, pin control 0 needs to point to a pin configuration node within a pin controller. This node has a list of configurations for one or more pins. In the example here, it configures the RX and TX pins for UART4. So to understand how to write this pin configuration node, we can follow the IOMUXC to its definition and find its compatible string. And when we find its compatible string, we can search the documentation folder for the device tree bindings for this node to look at the documentation. So if we search the documentation directory for the compatible string, we'll find this file. This file, to summarize it, provides the documentation, and it tells us that each entry consists of a macro provided by NXP for the pin function and an integer value for the pin setting, again, for the pull-ups or pull-downs. It provides information about the registers that are configured. I wanted to show you this so that it's available to you to use as a reference. But in the next slide, we'll see that thanks to NXP's naming convention, it's actually very simple to configure pins without having to dive into too many of these details. So to set up the pin function, NXP provides a header file with macros for all pins and their supported pin functions. The macros follow a naming convention that quickly tells you the pin name and the pin function. So by following the naming convention, it is simple to search the header file for a pin to find its functions. In this example here, we're configuring pin UART4TXD for function UART4DCETX. Alternatively, we could reconfigure this pin for another function such as UART2RTS or GPIO5IO29, for example. So when adding new pins, you can find the pin name in the datasheet or the reference manual, and then search this pinfunc header file for the specific pin macros for your application. The last entry in the FSL pins list is the pin setting. This allows us to configure, again, the internal pull-ups or pull-downs for each pin. The value is written to the pad control register, and the meaning of each bit is defined by the reference manual for the specific pin. In this example for pin UART4TXD, we can see bit 6 configures the internal pull-up or pull-down, and bit 8 enables or disables the pull resistor. So each pin will have a pad control register in the reference manual, and that the reference manual will define the values and options available for that pin. So to summarize the pin configuration node, each entry consists of a pin function and a pin setting. The naming convention for the pin function makes it really simple to find the right macro provided by NXP, and the pin settings are found in the reference manual for the specific pin that you are configuring. Okay, so now let's walk through adding an example device node. Generally, a process that you can follow for adding new devices is listed here. The first step is to identify the driver in the drivers directory. And then the next step is to just confirm that the driver is enabled in the kernel configuration. The next step, step 3, is to identify the device tree binding documentation for that driver. And then step 4 is to use that documentation to add the necessary nodes to the device tree. And then finally, in step 5, you'll want to install and test the new device tree file. So at a minimum, you'll need to rebuild and install the device tree file. You may also need to rebuild and install the kernel image and kernel modules if any drivers were added or modified. Okay, so the example we'll look at is to add a DS1337 real-time clock to the I2C bus on the ADEM Nano evaluation kit. When we do this, there's a few things we'll want to verify. Since the device is an I2C device, we'll need to make sure that the I2C bus is enabled in the SOM level device tree file. We'll need to make sure that the IOMUX settings are configured for the data and clock pins on the I2C bus. And then if the DS1337 device requires a driver, we'll need to make sure that the driver is enabled in the kernel configuration and that the driver is configured in the device tree underneath the I2C3 bus. Okay, so as I mentioned, the first thing we should do is just verify that the I2C bus is enabled. Looking at the top here, we can see in NXP's SoC device tree file, IOMUX8mn.dtsi, that the I2C3 bus node is defined but disabled by default. And then moving down, we can see in Variscite's SOM level device tree file that the device node is enabled, the status is set to OK. We can see that the pin control configuration is set up for the right pins and that the clock frequency is initialized as well. Note that there's also, for this I2C3 bus, there's also several devices on the SOM that are used on this bus, but for the purpose of this presentation, it was just removed from the screen here. And then moving down to our webinar device tree file, this is where we're going to add our carrier board device for the DS1337. Okay, so following our 5-step process, the first step is to identify the driver for our new device. There's several strategies for doing this. One of the strategies I like to follow is just to search the documentation directory for the device name. So in this example here, we can grep the documentation folder for DS1337. When we do that, we find a documentation file with a compatible string of Dallas, DS1337. And then to find the driver for this, we can use the compatible string to search the drivers directory. So here we grep the drivers folder for Dallas, 1337, and we find a device driver called RTC DS1307.c. So the next step is to enable, just to make sure that the driver is enabled in the kernel configuration. And to figure out what needs to be, to figure out the configuration string that needs to be enabled, one of the things I like to do is to search the make file in the same directory as the driver. So we can search the make file for RTC DS1307.o. And when we do that, we can find the configuration string that has to be enabled here, as shown. So in step 2, to enable the driver in the kernel configuration, we can run make menu config, and then we can select the driver. And after doing that, we can run make save def config and copy our updated def config file to IOMUX8 var def config for revision control in the future. Okay, so after we found our driver and we've enabled it in the kernel configuration, the next step is to identify the device tree bindings. And we did that again by searching the device in the documentation folder. So this here is the device tree binding for the RTC DS1337. We can see that the required properties are provided as well as the optional properties. And at the bottom, there's an example device node that we can use as a reference. So in step 4, we want to use this device tree bindings documentation to add a new device node to our webinar file. I want to highlight a few things here. The unit address for the device node for I2C devices needs to match the I2C address, as well as the reg property. So in this example here, we use the documentation on the left to add the new node on the right, and we can see that the I2C device is located at I2C address 68. And then finally, step 5 is to install and test the new device tree file on our target device. So after we've done that, we can boot up the new device tree file. And to test the real-time clock device, I simply just grepped the kernel logs for DS1307, and I saw that indeed RTC1 was registered using the RTC DS1307 device. We have a wiki page dedicated for our real-time clock that will walk you through more information about how to use and test the real-time clock interface. And then finally, this is our updated webinar device tree file. So we have the minimal device tree file that we created initially with the new I2C 3 node and the RTC DS1337 node underneath that. I mentioned this earlier. I also have additional examples for adding new device nodes, one for a PWM device and one for a PWM backlight device. They're attached to the end of this presentation. A PDF of the presentation will be emailed to everybody who registered and attended the webinar. So you can view those after the webinar if you want to see another few examples. A few debugging tips. If you find yourself in a situation where your device tree isn't booting, I like to recommend starting with a minimal device tree file that will boot, just like we did in the example here. Once you have a minimal device tree file that does boot, I recommend making small iterative changes and adding and testing only a single device at a time. And as you get things working and you're making small iterative changes, it's good to capture these changes in Git, so you always have something to revert back to. If your driver isn't probing, it can be helpful to verify that the driver is enabled in the kernel configuration. You'll want to verify that the device is enabled in the device tree and that status is set to OK. Verify that the device tree binding matches the documentation. Look for other examples in the Arch ARM64 boot DTS directory. And you can also use the /sys firmware device tree directory in the root file system to verify that your bindings match what was actually parsed by the kernel. It's also helpful to check dmessage for any errors or warnings that are related to the driver, similar to what we did for the real-time clock earlier. And then I just want to highlight that the workflow for making changes to a device tree and testing it only takes a few seconds or maybe 30 seconds. Again, we just need to run make DTBS, and then assuming you have networking working, we can SCP the updated device tree file to the target device and then simply reboot. And this will allow us to quickly make small iterative changes to our device tree and test them on the target device. Okay, so now next, let's look at integrating our device tree file with Yocto. So what we'll do for this demonstration is we'll set up a new Yocto environment, and then we'll create a kernel patch for the changes that we just made for our new webinar device tree file. And then we'll create a VB append for the kernel recipe to apply the patch and configure U-boot to boot our new device tree file. A few notes, generally it's best to create a Yocto meta or BSP layer for your project. Variscite has a blog post called Creating a Custom Yocto BSP Layer that you can reference for how to do this. But for this presentation, I'll just simply add the patches and VB append files to meta Variscite FSLC. Okay, so the first step is to set up a Yocto environment. Again, this just follows the standard process that's defined on our wiki, and there's a link here that'll walk you through and share more details as necessary. The first step is just to make a new BSP directory and then use the repo tool to clone and pull down all the code necessary for building Yocto. After we've done that, we'll create a new directory in the meta Variscite FSLC layer underneath the Linux recipes directory called files. And this files directory is where we'll add our kernel patch to. Okay, so now let's look at how to create a kernel patch that we can use in our Yocto layer. So to do this, let's change directory back to our Linux IOMUX folder. we can run git status, and we can see that the only changes underneath the Linux IOMUX folder are to the make file, where we added our new webinar device tree file, as well as a new device tree file called IOMUX ADEM and varsom webinar.dts. To create a patch file for this, we can run git diff, and then we can redirect the output to the files directory that we created on the previous slide, and we'll redirect that to a new file called add webinar device tree.diff. So after we've created our new patch file, now we can create a Yocto BB append file in the meta Variscite layer underneath the Linux directory. The first thing we do here is prepend the file's extra path variable to add the directory that contains our patch file. Again, that's that files directory. Then we append the source URI variable to fetch and apply the device tree patch. And finally, we add a few lines at the end to create a symbolic link in the boot directory so that uboot will boot the correct device tree file. So after creating the patch files and adding them to the Yocto layer, and then adding this BB append file, we're now ready to build an image and boot the new device tree file. Okay, so now let's look at how to build a new image with our updated kernel. So the first thing I like to do is to always clean the Linux Variscite recipe just to make sure we're starting from a clean place, and then simply run bitbake fsl image GUI. And again, the whole process for building the FSL image GUI for your hardware platform is documented fully on our wiki with a link listed below here. So just to summarize what we talked about, each board generally has a unique device tree file. A device tree specifies devices that cannot be discovered in a generic way. Device tree bindings describe the syntax and are available in the documentation directory of the kernel. In general, the compatible string is what matches device nodes to device drivers. And again, I want to highlight that there are many resources and examples both within the kernel as well as online. If after using and looking at those resources, you're still stuck, you can always request support through Variscite's customer support portal. Okay, so thank you for listening to the webinar. I'll now look at the questions, and hopefully I can answer any questions you may have. Okay, so one of the questions was, will an email be available to ask more technical questions if there's not enough time during this webinar? As I mentioned, Variscite has a customer support portal, so you can visit our variscite.com or the software wiki, which will link you to the customer support portal. You can sign up for that, and that allows you to ask questions directly to our hardware and software engineering team. Another question is, the IOMUX ADEM Plus reference manual does not provide the IOMUX pad register settings. Let's see here. One of the things you can do here is you can also use the pincomp header file that I mentioned within the kernel to see the IOMUX settings and options. You can also visit the documentation on our kernel and wiki to see the options and examples provided by Variscite for this. But again, I think probably the best thing to do is to look at the kernel header file, as I mentioned, the naming convention, and use that to find the proper settings. One of the other questions was, is it better to create a new device tree file or edit Variscite's device tree file directly? Generally, I like to make it as easy as possible to create and maintain your own device tree file so that as updates are provided by Variscite, you can easily merge these in. So I think it's always best to make a new device tree file. And then if your carrier board is very similar to Variscite's carrier board, you can include Variscite's carrier board device tree file. If it's significantly different from our carrier board, it might be better to create a new device tree file and then include the the SOM level device tree file, and then use our carrier board as a reference for adding new nodes. So again, I think it's best to create a new file, and that way you can easily merge in changes from Variscite. And just a note, when you do this, if you add a new device tree file, just like we walked through in the example here, you'll need to update the U-boot environment to boot this new device tree file. You referenced the documentation folder. Where can I find that? So within the kernel source tree, I think it's within the root directory of the kernel tree, there's a documentation folder. So you can search that documentation folder for the device tree bindings. There's actually a lot of helpful documentation in there for the kernel itself, the devices, the device tree bindings, etc. So it's I think it's in the root directory of the kernel source tree. Okay, so another question was, what are the M4 device tree files? So the IOMUX 8 SoCs, many of them, I think all of them actually have an integrated Cortex M4 or M7 processor. So the M7 and M4 device tree files are used when running the example firmware applications from Variscite and NXP. So since the A53 and M4 can't both use the same resources at the same time, the M4 device tree files simply disable the resources that are used by the M4 firmware example projects. So there's UART example projects, there's I2C example projects, etc. So those device tree files simply disable the nodes used by the M4 firmware. Okay, so I think that's all the questions for now. Thank you for joining the webinar. I hope you learned something. If you have more questions, feel free to register through the customer support portal and ask those questions directly to our engineering team. So again, thank you for your time.